Hey team, thanks to everyone for joining. I'm Alona Slastin and I'm an ML engineer at Software. I was wondering how I could describe my passion in work, and I think that I love everything that needs to be automated, anything that is still triggered or finished by hand. I think we all deserve to delegate the repetitive work on the machines, especially one that has to do with data. That's why today I would like to share with you one of the ways how to organize such pipelines with the help of GCP Cloud Pipelines. Let's start with agenda. So what we are going to discuss today is we will start with a small intro, then we will cover some general information about GCP platform and what it does. After that, we will get to know more about Kubeflow and TensorFlow Extended. We will discuss then characteristics of AI platform pipelines and how to build a model without data. Of course, it's impossible. So next, I will tell you a few words about data and model. And we will finish with the most interesting part, practice with Scikit-learn, BigQuery and TFX pipelines. Okay, let's get into business. Today, no one can argue that machine learning has found its way in all areas of human life, from social science to industrial enterprises. But the questions on how to properly organize the work of those ML models themselves are relevant as never before. In that view, I would like to present this talk about the AI pipelines on cloud, which significantly help managing ML workflows. And of course, I will show some examples of them. I'm sure you heard about other providers whose services can be used for similar purposes, Amazon, Azure, etc. But today, I would like to draw your attention to GCP Cloud Service. Enjoy the talk, and let's start. Nice to meet you, AI Platform. This is a Google Cloud Platform service that includes a set of tools for data scientists and data engineers. What's the use of it? It helps to streamline ML workflows and access the AI world. It's targeted especially at building, deploying, and managing machine learning models in the cloud. It can be used to train at scale, which is so important today, and host in the cloud. You're going to hear the word component quite a lot from me, and for that, I would like to give a definition for it right away. A pipeline component is a self-contained code that is responsible for one step in the pipeline. For example, data preprocessing, data transformation, model training, and so on. Components of AI platform. Let's start with the training service. This allows customized training with capability of different machine types to do training jobs, to enable distributed training, to do hyperparameter tuning, and to accelerate with GPUs and TPUs. You can submit your input data for AI platform for training using one of the built-in solutions. If it doesn't fit your case, there is a possibility to train an application and to run on your platform. You can also submit a custom container with your training application and its dependencies to run on your platform. Speaking of prediction service, it allows to serve predictions based on trained model, regardless if the model was trained on your platform or not. And finally, data labeling service. This means involvement of real humans to label a custom dataset, including video, image, and text data. To start using labeling service, a representative sample of labeled data must be provided, along with all possible labels and instructions for matching. Let's talk about ML workflow. In this chart, you can see a standard machine learning workflow. I think this is not new to many of you. And perhaps now you think that you can do everything using regular frameworks yourself. Why am I again discussing the topic of setting up pipelines if everything can be done locally in notebooks? Let's discuss this as we move to the cloud. A big part of it is covered by GCP AI platform, and these stages are iterative. You may need to reevaluate and go back to the previous step at any point in the process. Let's go through them and find the main characteristics. Data intake, sourcing and preparing your data. Model initiating and training. Users can develop the models in 2 steps using different tools: BigQuery, Dataflow, Python, etc., and include them into AI pipeline steps. The AI platform provides the services you need to train and evaluate your model in the cloud. For example, hyperparameter tuning functionality to optimize the training process. Model deployment. You can host your model in the cloud. AI platform provides tools to upload trained ML model to the cloud. In order to deploy your trained model on AI platform, you must save your trained model using the tools provided by your machine learning framework. This involves serializing the information that represents your trained model into a file, which you can deploy for prediction in the cloud. Sending inferences to your model. AI platform provides services that you need to request predictions from your model in the cloud. There are 2 ways to get predictions: online or stream prediction and batch prediction. I would like to add a small spoiler here. For example, BigQuery ML allows us to get only batch predictions. It's all boring. But if you export this model to AI platform, you can create pipeline with online predictions as well. And that is a good bonus. In most cases, you pass input data to a cloud-hosted ML model and get inferences for each data instance. Monitor your prediction service. We all agree that keeping an eye on how the forecasts are being run is important. AI platform provides APIs to examine running jobs. In addition, various Google Cloud tools support the operation of your deployed model such as cloud logging or cloud monitoring. Manage your models and model versions. AI Platform provides various interfaces for managing your models and versions, including a REST API, the Google Cloud Command Line tool, and the Cloud Console. Okay, Kubeflow. So what is a pipeline? It's a ML workflow graph that includes all necessary components and rules for combining them. It includes descriptions of inputs and outputs, like parameters, data, results, etc. Kubeflow, Kubernetes. I'm sure many people have heard these names in their work. I think most often from DevOps and data engineers. Let's talk about what Kubeflow pipelines means for data scientists. Kubeflow Pipelines is a platform for building and deploying portable, scalable ML workflows based on Docker containers. The Kubeflow Pipelines platform includes a user interface for managing and tracking experiments, jobs, and runs, an engine for scaling multi-step ML workflows, an SDK for defining and manipulating pipelines and components, notebooks for interacting with the system using the SDK. And goals of Kubeflow pipelines we can describe in 3 easiest. First one, an easy end-to-end orchestration, as in simple setting and controlling of machine learning pipelines. An easy experimentation, making it easy for you to try numerous ideas and techniques and manage your various experiments. And an easy reuse, enabling you to reuse components and pipelines that will help you to quickly create end-to-end solutions without having to rebuild from scratch every time. TensorFlow Extended. Managing steps in ML workflow can be difficult and time-consuming. TensorFlow Extended is an end-to-end platform for deploying production ML pipelines. It allows an easy implementation of MLOps using different orchestration toolkits, such as Apache Airflow, Apache Beam, or Kubeflow pipelines. To be honest, when I first saw TFX code and pipelines, I got a bit confused and somewhat taken aback. It seems very complicated and not quite logical for me. However, step by step, component by component, I explored the entire structure of the pipeline. And then I realized that I was completely and absolutely loving it. This framework made my life easier as an ML engineer, and not only mine. TFX pipeline specifically designed for scalable, high-performance machine learning tasks. By implementing your workflow as a TFX pipeline, you will automate your ML process, which lets you regularly retrain, evaluate, and deploy your model. Utilize distributed compute resources for processing large data sets and workloads. Increase the velocity of experimentation by running a pipeline with different sets of hyperparameters. You can see all available components on the screen that can be built with TFX libraries, and you can use all of them together or separately. I will not go into details about these components now. We will continue discussing TFX later. So, many of you have heard about applying DevOps practices to ML, the MLOps. How it can help? The impact can actually be huge. This means a fully automated, managed, and importantly, transparent ML workflow. AI platform pipelines helps you implement the MLOps by providing an interface where you can manage steps in your workflow as a pipeline. The ML pipelines are portable and reproducible definitions of ML workflows. So, to sum up, what we just discussed is that Kubeflow pipelines can be used for monitoring, auditing, and managing ML pipelines on Kubernetes, and SEP TFX is used for creating ML pipelines and orchestrating end-to-end ML workflows. Okay, can we agree that it's helpful, isn't it? But why would I want to use something else on top of Kubeflow? Isn't that enough? Well, actually no, it's not enough. Here comes the AI platform pipelines that makes our life easier when we want to get started with MLOps, as it saves you from all that headache of setting up Kubeflow pipelines with TFX. AI platform pipelines helps you with all necessary background for the project. Setting up a Google Cloud Kubernetes cluster, creating a cloud storage bucket, and installing Kubeflow pipelines. With AI platform pipelines, you can set up a Kubeflow cluster in 15 minutes, so you can quickly get started with ML pipelines. There are a handful of major cloud services, but lots of smaller platforms. To me, it seems that there is no certain bidder. Each one of them is best at their specific task. But when we talk about choosing one provider or another, our decision has to be always based on the objectives of the project, team complexity, and possibly even more by the already created architecture. For comparison, I went with the non-mainstream platforms, Azure ML, Amazon SageMaker, and it's not hard to guess which else, GCP AI platform. They all support creation of ML pipelines. So, I know my data scientist colleagues are keen users of all sorts of clouds. Hence, before this talk, I asked my team to fill the survey by which they will rate their experience when using different features of these platforms. Besides general feel of using cloud services, I want to see which criteria, if any, are the most sensitive for our data science professionals. Of course, I would like to clarify right away that results of such comparison by no means will force you to use one provider over another, or will declare an absolutely perfect platform. I'm 100% for that any difference in comparison them should be essentially reduced, and the balance was found, as it will benefit all of us, okay? Okay, then I will briefly go over the results. So I asked it a simple question to say how happy a data scientist was with a cloud service provider for this or that specific feature. In many fields, all three platforms were not at all different, like deployment operation, simplicity of setup, or data orchestration. Perhaps because these operations have become standard. And actually, this is where GCP's AI pipeline should shine, as I just explained. Of course, GCP is just getting attention, and to be fair, not many of my colleagues had got a chance to use it yet. However, we started seeing some minor variation without a clear leader. No one likes reading documentation, obviously. But mostly, people are feeling positive about managing everything on the cloud. In terms of adopting new technologies and its own learning curve, both GCP and its closest competitor, Amazon, demonstrates golden standard of services, while Azure in the projects is still treated with special care and consideration, especially in data science related tasks, like taking care of model performance and fine tuning. Anyway, I thank my colleagues for taking time to participate in this survey, and I see that GCP pipelines are warmly welcomed by them. All right, everything sounds beautiful in theory and from others' opinions. But is everything that simple in practice? Let's check together. As I would not use the word simple here, but rather interesting. First of all, I want to add a few words about the data source being used. It contains retail data from American chain Walmart, and the purpose of forecast was to estimate a unit sales. So the target value is the demand. Based on this data, a list of features was generated that you can see on the screen. Let's bring in scikit-learn. Many of you have heard of scikit-learn. It's a famous open source library for ML. Besides supports of supervised and unsupervised learning, it also provides various tools for model fitting, data preprocessing, model selection and evaluation, and many others. We can use scikit-learn inside the AI platform pipelines to help define the model. The pipeline uses a mix of custom and pre-built components. You can add existing components to your pipeline. This may be components that you create yourself or that someone else has created and made available. We name them pre-built components. Python function-based components make it easier to iterate quickly by letting you build your component code as a Python function and generating the component specification for you. Let's dive deeper and see how to do it. So here is Google Cloud Platform console. I will go to AI platform, open notebooks. I already started the one which we need and open it. This notebook is created for our two pipelines, BigQuery and scikit-learn. And The first one I can open. So the source for prebuilt components is that repo. So we can find components here. For example, for BigQuery. And all necessary documentation also is available. We define it's a component store using KFP component. Then we create pre-built components. The pipeline uses the following pre-built components that are included with KFP distribution. BigQuery component to submit a query to BigQuery and store result in a cloud storage bucket. AI platform training component to submit an AI platform training job as a step in a pipeline. And the last one, AI platform deploy component to deploy a trained model from a cloud storage location to ML engine. Then we define custom components. The pipeline uses two custom helper components that encapsulate functionality not available in any of the pre-built components. The components are implemented using the KFP SDK's lightweight Python components mechanism. The code for these components is in the helper components file. Retrieve baseline. The component retrieves a tuning metric and hyperparameter values for the baseline of AI platform training hyperparameter tuning job. Evaluate model. This component evaluates a scikit-learn trained model using a provided metric and testing dataset. After that, we define our pipeline steps using these components. For example, create training split using pre-built BigQuery component. Create validation split with same component. Hypertune pre-built train component. And evaluate model with our custom component. Before deploying to AI platform pipelines, the pipeline DSL has to be compiled into a pipeline runtime format, also referred to as pipeline package. The runtime format is based on Argo workflow, which is expressed to YAML. We take the latest base and trainer images from the cloud build, and they automatically redeploy if any changes go to repository. Then we can deploy pipeline package using just created YAML file and submit the run. We can submit the run using command line or using UI. In this case, I will use command line. I already ran this pipeline, so we can monitor running status. I will go to the same console, open pipelines, and then go to Kubeflow dashboard. Usually here, all our pipelines is available. Then I will go to experiments, all runs, and then file our run sklearn pipeline. Here the whole structure of our pipeline is available with all necessary information. For example, let's investigate BigQuery component. Here is our dataset ID, Google Cloud Storage root, project ID, etc. And also output artifacts, output parameters. For example, here is creation of validation dataset. Also, the most interesting, I think, this one, submitting a CloudML training job as a pipeline step. We can find here our HyperTune settings and our job ID. Also, we can go to this job ID and see results. Again, I go to the platform, open jobs, ID is this. So we should find it here. Okay. Here is it. And in this job, all our HyperTune trials is available with their hyperparameters. And the first one is the best one with metric and also elapsed time. I think we can go to the next one. BigQuery ML. It's a GCP service with ability of creating and executing ML models in BigQuery using standard SQL queries. BigQuery ML simplifies machine learning by letting SQL practitioners build models using existing SQL tools and skills. BigQuery ML increases development speed by eliminating the need to move data across of BigQuery ML. It's working with SQL. You don't have to use multiple languages, and everybody who is used to interact with an SQL database should be able to use it. You can serve your models directly from BigQuery. No need to manage a workflow that will feed, train, and serve an external system. It's saving a lot of MLOps work. It's quick and easy to test. You don't have to extract data to your local machine to give it a try. Easy to be an expert machine learning engineer in order to execute a model and get good results. And documentation is really good. Everything is detailed and it contains tons of examples. Console BigQuery ML. BigQML can be a bit of black box. It's hard to know what it does under the hood. Hopefully, they have inspection functions to get some insights, which makes it hard to optimize your dataset before injecting it to BigQuery ML, or to fine-tune your models using the various options. It's less flexible. If you are an experienced data scientist who is used to work with Python or R and in tons of libraries, you will probably feel limited. There are so many ML models out there that are not available in BigQML in terms of libraries to optimize the models, but I hope this is just for now. And it has its limitations. BigQML supports not all ML models. Let's go to the notebook and try pipeline with BigQML. I will open the same notebook instance, and another notebook. Just like this example with scikit-learn, we can use pre-built and custom components. For this pipeline, only one pre-built component was used for deploy. We are not able to use pre-built BigQuery component because it doesn't support create model statement. But it's not a problem because we can easily create our own. Then we define custom components for evaluation, training, and exporting model. After that, we use these components to create our pipeline and compile it. Everyone who has heard something about BigQuery knows that it's only supports batch predictions. And in general, why do I need to create a whole pipeline if I can do it all directly in BigQuery itself? The answer is easy and important. When the model is deployed to the AI platform, online predictions became available. So now we have continuous trained model with ability of online prediction using standard SQL. I also pre-run this job and we can investigate results together. Again, I will go to Kubeflow pipeline dashboard, open experience, all runs, and find our run BigQ pipeline. We can also investigate some components together. For example, export model. Here is our Google Cloud Storage root, our created table, created model, and the path and the query command also. Okay, let's investigate, in my opinion, the most interesting type of GCP pipelines. TensorFlow Extended, a great MLOps tool with a flow pipeline for building a robust and transparent machine learning system. When used correctly, it makes your ML work easier by making cutting-edge machine learning performance while reducing MLOps technical debt. In general terms, there are 4 main tasks of MLOps work: sampling, training, evaluation, and maintenance. Each of them requires a deep dive into details, organization, and requirements. This whole process is complicated by the fact that over the time, the data changes, new trends and distributions appear, the model becomes outdated. As a result, after a certain period of time, the result of our work is simply an archive of versions of the models, which no longer give sufficiently accurate results. This means that the main goal of the development of ML pipeline is the generation of stable forecasts. Key fixed benefits: careful orchestration of ML model components. You are empowered to keep track of your components within a DEC pipeline. You can understand a new ML project quickly and understand how each component works in tandem to produce robust ML production model. Simplify quick and control changes to meet business needs. You can quickly detach and edit relevant components to meet business needs. And consistent valuation of business and production metrics. Validator and evaluator components ensure your new model is robust and more reliable than your previous ones, even during automated pushes. I have always agreed with the opinion that it's better to see once than to hear to everything in theory several times. So let's get back to the notebook and Kubeflow dashboard again. For this time, I will use another notebook. For opening them, I will go to AI platform on the Google Cloud Platform console, here with Z. And we will start with going through all components. Okay. I think you will love it with I. Let's start. The first phase of ML development process is data loading. The example gen component ingests data into a tfix pipeline by converting different types of data to TF record or TF example. And here is the structure of this component and code for defining it. The next step is to explore our data, visualize it, and validate it for possible inaccuracies and anomalies. The statistic gen component generates a set of useful statistics describing our data distribution. And as you can see, it receives the output of example gen. Here is the code for defining it. Also, we can visualize statistics for our training split and evaluation split. Some TFX components use a description input data called schema. SchemaGen automatically generates the schema by inferring types, categories, and ranges from the data statistics. The SchemaGen component generates the schema using the statistics for the train split, and we can configure this component here and see our data schema for numeric features and categorical. The example validator component identifies anomalies in data. It identifies anomalies by comparing data size statistics computed by StatisticGen against a schema generated by SchemaGen or imported node. And here is the code. Also, we can see that our evaluation and training splits without anomalies. The transform component performs data transformation and feature engineering. To configure transform, you need to encapsulate your preprocessing code in the Python preprocessing fn function and save it to a Python model that is then provided to the transform component as input. And we can configure transfer component using this code. The trainer component trains a model using TensorFlow. To configure trainer, you need to encapsulate your training code also as a Python model. And here is the definition of that component. The tuner component makes use of Python Keras Tuner API to tune your model's hyperparameters. It integrates with transform and trainer components for model hyperparameter tuning, continuous training pipelines, as well as advanced use cases such as feature selection or feature engineering and model architecture search. And here is definition of this component. Then we can retrain our model, the best hyperparameter set. And the evaluator component analyzes model performance using the tfix model analysis library. And here is configuration of it. Our evaluation matrix. And we can check our model performance validation status and go to the next component. Compared to the evaluator component above, which validates a model performance, the infravalidated component is validating that a model is able to generate predictions from solved examples with an environment configured to match prediction. And here is the code and our chicken. And the last one component is pusher. It checks whether a module has been blessed, and if so, deploys it by pushing the module to a well-known file destination. And here is configuration. After we figured out the components, let's move on to creating the pipeline project. Project itself contains of several files: config file, pipeline file, preprocessing file, module file, runner file, and features file. As you may have understood, you put all components that we considered earlier in the pipeline file and organize the pipeline itself as follows. The order can change if the component dependencies are not related. Let's go through Notebook and see how to create a pipeline. I will run it with you also. First of all, we update our environment variables, review our working directory. Okay. Move to our working directory. Set our environmental settings and variables, and compile our pipeline code and deploy our pipeline container to AI platform pipelines with prefix CLI. Here is command for creating our pipeline and creating monitoring using this command. Okay, I also predefine this run so we can investigate it together. It's here. I will open. Okay, here is all our components, also with some input parameters, output parameters, and artifacts. And we can go through them if needed. This run is without hyperparameter tuning. If we change our enable tuning parameter to true and recompile our pipeline code, then we can use hyperparameter tuning. I think continuous training, I'm sure that continuous training can be implemented by adding a training schedule or by integrating CI/CD and status retraining when the source code changes. So I will show you how to create a run of our pipeline using UI and create some scheduling process. We should choose a pipeline. We just create it and run. Create, select running. I will add HPU here. Select experiment. It's on 11. And select runtime one of only one run or recurring if you want to create some trigger and scheduling. For example, run every 1 week. We can also add some parameters. And press start. And now our pipeline run will run every 1 week. If you are thinking, now I want more, then this slide is for you. Don't limit and try something new today. We are glad to welcome all new specialists, and if you are interested, just contact our team. So thank you for the time. Have a nice day and move to the cloud.